Hello, my voice is clear to you all? Okay. હલો. ઓકે એવું છે. અરે કઈ sorry. Listen everyone. In last lecture, RSA proof is done everyone. Hello, RSA proof is done everyone. How we are getting see how we are getting exactly the plain text that means that particular proof that I have explained in your class. See, in offline and online, in both the place, it is in parallel. It is working, so that's why I forgot that. So please reply me. Is it done? The proof of how to get the plain text. I think it is done, right? Rikin, can you hear me, everyone? Okay. So is it done, Abhi? That proof regarding means how you are achieving this plain text and just wait. I will share the material and show you. Please reply me. I'm sharing my screen and tell me whether it's done in your class or not. Okay, listen, this proof regarding how we are getting this plain text, right? And all these cases, is it done in your class? Hello? Yes, one example of RSA last time you have done, Abhi, you are correct. But see, this proof is done. I think it done. So please see that material and please reply me. These all cases I have explained. Just wait. There is a one call. Okay, so Abhi, all these three cases are done, right? Okay, so I'll explain you. Just wait. Okay, so okay, everyone. So it's done. So today I will start with the new topic. So see, suppose let's say there are two party, Alice and Bob. The Alice wants to send some message to a Bob. So all of you know that in public key crypto system, the Bob has to run the setup, right? And all of you know that in RSA algorithm, the Bob choose a two large prime number that is n equals to p cross q. But see, the question is how to get this large prime number. So suppose the Bob wants to 512 bit prime. So but see, there is no algorithm. So what we can do, we can do the primality testing. We can do the primality testing. So you can say that we could just choose a large random number and test it to be sure that it is a prime or not. So see, simply here I am writing. So let's say here I can say that the randomly generated number. Okay, so randomly generated number that I am taking, and then the testing for primality. Testing for what? Testing for primality. Okay, and see these, you can say that these are black box. Okay, and what it will give you output, whether yes or no, means whether it's a prime or no. So that means see, in your lab session also you have to do the same thing. So if you want to first perform the RSA algorithm, so whatever the number that is entered by the user, first you have to check whether that number is a prime or not. So randomly we are generating some number, and then we are applying some primality testing, right? So like in deterministic algorithm, see the normal, all of you know that how to get the prime number. You, if you want to check whether the number is a prime or not, right? So this condition that we are checking, and based on that it will give you yes or no, right? So simply I want to say that is the finding an algorithm to correctly and efficiently test a very large integer and output a prime or a composite, whether the number, whatever the number that is entered by the user, whether it's a prime or composite, has always be a challenge in the number theory. So algorithm that deal with this issue, that can be divided into two broad category. So see, there are two types of algorithm. One is what? So here I am writing, one is a deterministic, and another is a what? Probabilistic. So there are two type of algorithm, deterministic and probabilistic, or you can write the randomized. Okay, deterministic or probabilistic, deterministic, and another is a probabilistic, or you can say randomized algorithm. So now what's the difference between this deterministic and probabilistic? So the deterministic, see that normally we are using that approach that is deterministic. It always gives a correct answer, right? But while in the case of probabilistic, I can say that an answer that is correct most of the time, but not all the time, right? So the deterministic algorithm that is less efficient than the probabilistic, it takes more time to check, right? And in the case of deterministic algorithm, it accepts an integer and always output a prime or a composite. While in the case of probabilistic, see here in the case of probabilistic, there are two types that here I am writing. There are two types. One is what? One is one, you can say that that is just wait. Las Vegas, and another one in that is Monte Carlo. So again, I repeat, see, algorithm that deal with this issue for finding a check whether the number is a prime or not. See, there are two approaches. One is a deterministic and another is a probabilistic. Deterministic means it always gives a correct answer. In the case of probabilistic, you can say that answer that is correct most of the time, but not all the time. In the case of deterministic, you can say that it is less efficient than the probabilistic. And in the case of deterministic, the algorithm accept an integer and always output a prime or a composite. While in the case of probabilistic, there are two types. One is a Las Vegas and another is a Monte Carlo. So now in the case of Las Vegas, what? So here in the case of, see, I am writing here, in the case of what is Las Vegas. So in the case of Las Vegas, you can say that the algorithm may not give any answer, but if gives it will be correct. So in the case of Las Vegas, you can say that the algorithm may not give any answer, but if it gives, it will be correct, right? While in the case of Monte Carlo, so here you can say that, see, the scenario is in the case of Monte Carlo, here you can see that there are two algorithms are there. One is a one you can say that is probably Fermat primality testing, and another is a Miller-Rabin test. These are the two types of algorithm. And in a Monte Carlo, here you can say that just see here, actual the number is a prime, but what the algorithm says, the algorithm will give prime 100%. And while here but here you can say that it will give, it is a prime, but what, with error epsilon, and here with 1 minus epsilon, right? Approximately 1 minus epsilon. So listen, here in the case of, you can say that the Las Vegas, the algorithm may not give any answer, but if it gives, it will be a correct. While in the case of here, you can say that actually, see, basically the purpose to find out whether the number is a prime or not. So here you can say that if actually a number is a prime, but algorithm will give a prime that is a 100%, right? But composite it is 0%, and actually the number is a composite. But see, here you can say that the probabilistic algorithm in this category, it return either a prime or composite based on this particular rule. If the integer to be tested is actually a prime, and the algorithm definitely returns a prime. Okay, and the second case is if an integer to be tested is actually a composite and it returns a composite with which probability, with a probability 1 minus epsilon, but may return a prime with a probability epsilon. So the probability of the mistake can be improved if we run the algorithm more than once with a different parameter and using the different method. So if we run the algorithm n times, then you can say that the probabilistic of the error may reduce to what? Here you can say that it may reduce to this term, right? So up to this clear, everyone? Is it clear to you all? Now see, up till now, all of you know that up till now you have learned this deterministic. Just wait, I am writing this deterministic algorithm. So now see here, here I will not explain in detail how you are getting the complexity, right? Just see, up till now you have learned this deterministic algorithm. In that, simply, if you want to write the logic for prime, if you want to check whether the number is a prime, then all of you know that in semester 2 you are using this uh, uh, just use this logic. I equals to 2, then I less than equals to n minus n by 2, I plus plus, right? And then if the number module by I that is equal 0, then I am writing it's a not, right? So these are simple logic, all of you know that there is no need to explain, right? So up till now we have used this deterministic this particular this type of algorithm that you have understand. So now see here the complexity is what, this one. But see, suppose let's say assume there are 200 bits, then the number of bits operation need to run this divisibility test is what, 2 raised to 200. Now see, now this algorithm further, how can you improve it? So see this, I can improve this algorithm by writing in this way: for I equals to 2, I less than equals to root n, I plus plus, right? So now see, if you are improving my algorithm, so at that time I can say that my complexity is this. So that means you can say that again the number of bit operation need to run the divisibility test algorithm is 2 raised to 100. So now see, up till now what I want to try this, if the given number is given to you, if you want to check whether the number is a prime or not. So there are two types of algorithm that I have explained. One is a deterministic approach and another is a probabilistic method. So this type of deterministic algorithm, up till now you have learned by using this logic you are checking whether the number is a prime or not. If you are checking in this way, so here you can say that the complexity is this: how many, if the n is 200 piece, then the number of bit operation need to run this divisibility test is 2 raised to 200. But if here I am improving my algorithm, then I can say that the number of bit operation need to run the divisibility test is what, 2 raised to 100. So that's why one algorithm is there that is known as a AKS algorithm, right? So AKS algorithm in 2002, Agarwal, Kayal and Saxena, by using three person, they announced that they had found an algorithm for primality testing with polynomial bit operation time complexity, and its complexities I am writing, see here, so O log 2 and b raised to 12, right? So this is the complexity. So within that it will solve it within this time, it will solve this algorithm, right? So now see, this all about this deterministic algorithm, everyone. Now next is a probabilistic method. Okay, so in the case of probabilistic method, what do you just wait, I will open that. Okay, so see, up till now you understand one of the algorithm, that is Las Vegas. So in that I have explained you the algorithm may not give any answer, but it will give if it will be correct. Okay, but it gives it will be correct. So in the Monte Carlo algorithm, the two format primality testing in your left session, either you can if first if you want to implement the RSA algorithm, first whatever the number that is inserted by the user, first you have to check whether that number is a prime or not, and if the number is prime, then you have to consider that number for RSA algorithm. So in that whether you can implement the format primality testing or Miller-Rabin primality testing, both the approach is fine, right? Based on that you can implement. So now what is Fermat theorem? So all of you know that if n is a prime, then a raised to n minus 1 mod n, that is equals to 1, where the GCD of a comma n, that is 1. All of you know that. So that is, you can say that a and n are what? Co-prime. If the GCD is 1, means a and n are co-prime. So here I can say that select a random value of a such that the GCD of a comma n, that is equals to 1. Okay. Now, if a raised to n minus 1 mod n, that is not equals to 1, so then implies, you can say that n is a composite. And if a raised to n minus 1 mod n, that is equal 1, means here the n is a prime, but here you can say that n is probably prime. So to ensure this correctness, what we have to do, we can run this algorithm multiple times. Means first time I am running the algorithm says the number is a prime. Again I am run the algorithm. Again the algorithm says the prime. So many times if I am running my algorithm, and if my algorithm says it is prime, then I can say that the number is a prime. Okay, but see, it may be possible that suppose the 3 times I am run my algorithm, so the algorithm say prime, but at in the when fourth time I am implementing, so my algorithm return it is composite. So then I can say that my number is a composite, right? So that we will see in the Miller-Rabin algorithm, so you can understand everyone. Okay, so this is all about the Fermat primality testing. Now the next, that is a Miller-Rabin test. But see, before I explain you the Miller-Rabin test, first I will explain you the square root test method. Okay, so in the case of square root test method, these are the conditions that you have to write. So all of you write down, and based on that I will explain you. So before I explain you this Miller-Rabin test, first you have to understand the square root test, because Miller-Rabin test is based on the square root test. Okay, so this is a one way by check whether the number is a prime. For that is a what? That is a Fermat primality testing. Now second, that is Miller-Rabin test for to check whether the number is a prime or not, but it is based on a square root. So how to see this type of how to calculate the square root. So there's two conditions that you have to remember. If n is a prime, then the root 1 mod n, that is equals to plus or minus 1. And if n is a composite, then root 1 mod n, that is equals to plus or minus 1, and possibly the other values. So write down this 2 point, everyone. So this type of find out the square root, this type of question can be asked in exam. So what you have to do, if the number is a prime, then the square root of 1 mod n, that is equals to plus or minus 1. This answer you are getting. And if your number is a composite, then square root of 1 mod n, that is equals to plus or minus 1, and possibly some other values also you are getting. Okay, so now we'll solve that example so you can understand everyone. Up to this clear, everyone? Hello, is it clear to you all up to this? Okay, now I am writing the question. This type of question can be asked in exam. What are the square roots of 1 mod n if n is 7? Right? Now see what you have to do, everyone. The question is, what are the square roots of 1 mod n if the n is 7? Right? So now see, if so according to our algorithm, see, our algorithm is, if n is a prime number, then the square root of 1 mod n, that is equals to plus or minus 1. Your answers would be what? Plus or minus 1. So now let's check whether we are getting plus or minus 1 or not. So 7 is a prime number. So that means our answer finally at the end, what is our answer? Our answer is plus or minus 1. So now what I am doing here, so I am writing in this way, square root of 1 mod, right, n means 7, that is equals to, let's say I am writing, let's say I am writing this way, square root of 1 mod 7 congruence, let's say x. Okay, now what I'm doing here, the x square, right? So I'm writing both the side, I am doing performing the square. Now what happened? So now here it's a 7, means from 0 to 6. From 0 to 6 value you can take, right? So 0 I'm not taking. Okay, because now see the example that I have calculated so you can understand. And first we'll solve the another example. So now see here one example is given to you. First of all, mode 7 means 0, 1, 2, 3, 4, 5, 6. Now then after what you have to do, one by one you both the value that you have to take. So now what you have to do, so first you have to take the 1 and minus 1, both the value that you have to take. So 1 square more 7, then what you are getting 1, minus 1 square more 7, that is equals to 1. So now see in this way what you have to do. So first what I am doing, initially the value of x that I am taking, that is x equals to 1 that I am taking. If I am taking x equals to 1, then what I am getting here, so 1 square mod 7, so I am getting 1. Now then after I am putting x equals to minus 1, so again what I am getting here, I am getting sorry, just wait. Sorry. So see, if you want to find this square root of 1 mod 7, if 7 is a prime number, then final answer, that is what, plus or minus 1. Now I want to check whether I am getting plus or minus 1 or not. So what I am taking, so one by one, see here I am taking 1 plus 1 minus 1, both the value that I am taking. So what I am doing, 1 square mod 7, that is 1, minus 1 square mod 7, that is 1. Again 2 square mod 7, that is 4, minus 2 square mod 7, that is 4. Again plus 3 and minus 3 that I am taking, right? But see when I am performing 4, so see here 4 square mod 7, that I am getting what, 2. So that is, you can say that uh, 5 square mod 7, that is what I am getting, 4. 6 square mod 7, that is what I am getting, 1. So now see that is same as what, minus 3 square mod 7. Similarly this same as what, minus 2 square mod 7, and this same as what, minus 1 square mod 7. So that means here I can say that, see, just you have to check for what, just we don't need to test for 4, 5 and 6, right? So just here you have to check for what, only 1, 2 and 3. So now check from plus 1 to plus 3. So when I'm checking for plus 1 to plus 3, so at that time what I'm taking here, so see 1 square mod 7, that is 1 I am getting, minus 1 square mod 7, that is 1 I am getting, right? But see here I can say that sorry, sorry. Now listen everyone, here from that you have to check whether you are getting 1 or not. So here in this particular place I am getting 1, right? So now what we have to do here, so here only the square roots are what, plus or minus 1, right? Because the 7 is a prime and minus 1 mod 7, it is same as 6 mod 7, so you don't have to consider this 6. All of you clear everyone what I'm trying to say? Is it clear to you all? So again, see, I'm explaining this example so you can understand. If this type of question is given to you, so you have to write in this way. See here, what you have to do? Just you have to write Sorry. See, first of all, if you want to find the square root of what where n is given, n equals to 7 is given, and the question is find out the square root of root 1 more 7. So first you have to initialize with this root 1 more 7, that is congruence x. Right now, what I'm doing here, so both the side I am performing the square. So I'm writing in this way: x square congruence 1 more 7. Right now, what I am doing here, one by one you have to take the value. Right, from you have to start from mode 7, means 0 to 6 value. That 0 we can't take, so that means, see, let's say I am putting x equals to 1. So now see, what is the meaning of x square congruence 1 mode 7? So that means if I am performing x square mode 7, then what I am getting 1. Right, that is my answer. So now one by one I am putting all the value. So when I can say the x square is congruence 1 more 7, so if I am performing x square mod 7, then that is equals to 1. So what I'm doing here, x equals to 1, that I am taking. Right now, the 1 square mod 7. So 1 square mod 7, that means what I am getting? So I am getting 1. So that means this condition is true. Now again, what I am doing here, x equals to minus 1, that I am taking. So again, minus 1 square mod 7, that means what I am getting? 1. So that means, see, x equals to 1 and x equals to minus 1, these are part of my result. Again, now see, you have to check for x equals to 2. But see, when I perform 2 square mod 7, so what I am getting? I am getting 4, right? And it is not equals to 1. So that means the 2 is not considered. Again, minus 2. In this case, also I am not getting the 1. Right? It is not equals to 1, so it is not considered. Now again, you have to check what x equals to 3. Right? So x equals to 3. Is it a part, everyone? And x equals to minus 3. Are you getting 1? Yes or no? Yes or no, everyone? No. So that means here you can say that 3 square mod 7. So I am not getting the correct answer. So x equals to 3 and x equals to minus 3 is not considered. Okay. Now here I can say x equals to 4 and x equals to minus 4. Right. So that I am not considering it, because what, 4 square mod 7, that is 16 mod 7. So that is not equals to 1, because see here, when I can say x square is congruent 1 mod 7, if x square mod 7, that is equals to 1. Right, then I can say that x square is congruent to this. So in this case, I am getting one answer. 2 I am not getting, 3 I am not getting, 4 I am not getting. So now what I am calculating? 5 I am calculating. So x equals to 5 and minus 5, I am not getting the answer. Right, now I am taking x equals to 6. So now see here, x equals to 6. X equals to 6 means 6 square mod 7. Right, so 36 mod 7, then what I get here? 1. So that means this condition is satisfied. Right, so x equals to 6, then I can say that x equals to minus 6. Again, I'm getting this result. But see, here only the square roots are plus 1 and minus 1. Why? Because here I can say that the 6 is congruent to minus 1 mod 7. So either I am taking minus 1 or 6, both are same. Similarly, here I can write minus 6 is congruent to 1 mod 7. Right? So that's why here I can say that that's why I'm not considering this. I'm not calculating it for 4, 5, and 6. Right? So that's why the answer is what? Plus 1 and minus 1. Is it clear, everyone? Is it clear to you all how I have calculated? Right? So here, that point that I have written, I have calculated this value, right? But here in this case, what happened? So in this particular case, I am getting 1, right? But see, now if you are calculating for 4, 5, I am getting the same answer as minus 3 and minus 2. and in 6 square I'm getting 1, right? But here in this case I can say that this thing, the 6 is congruent to minus 1 more 7, and minus 6 is congruent to 1 more 7, and that's why the answer is plus 1 and minus 1. Now see this algorithm everyone. If n is a prime, then you can say that the square root of 1 more n, that is equals to plus or minus 1, right? So now we are getting the answer. Now the second example. Now you have to tell me the answer everyone. So see the aim. What are the square roots of 1 mod n where n is 8? So now all of you know that n is a composite number, right? If it's a composite number, then in this case, you can say that what we get, the square root of 1 mod n, that is equals to plus or minus 1, and possibly some other values that you are getting, right? So now how to check it? So please reply everyone. What we have to do here? So square root of 1 mod n, that is equals to x. Congruence, right? Now I'm both the side I'm performing the square. X square congruence 1 mod 8. Right? Now what I'm doing, one by one I'm putting all this value. Right? So initially I'm putting x equals to 1. When I put x equals to 1, so what I am getting? 1 square mod 8, right? 1 square mod 8 means I am getting 1. Similarly, in x equals to minus 1, also we are getting what? 1 answer. Now x equals to 2, so at that time what we are getting? 4. But actually when you can say the x square is congruent to 1 mod 8, if x square mod 8, that is equals to 1. So x equals to 2 is not included because I am getting 4, right? X equals to what? Minus 2, again I am getting 4. Okay, I am showing you the different scenario. So now then after, see if I am taking x equals to 3, so 3 square mod 8 means I am getting 1, means 3 is included. X equals to minus 3, so at that time again what I am getting here, I am getting 1. Okay, x equals to 4, that is not taken because it is not equals to 1. Then again x equals to 5, so what I am getting? 5 square mod 8, so I am getting 1. Again x equals to minus 5, so in that case also what I am getting? 1 answer. Now x equals to 6 is taken? No. At minus 6. So now see, because here the n is 8, so from 1 to 7 that you have to check everyone. Okay, so now when I'm putting x equals to 7, so that is 7 square mod 8, that is equals
We are
to
delighted
1.
to present to you.
In minus 7, also it is 1. Now please reply everyone, which are the solutions here? Which are the solutions? What is the answer? Please reply in the chat window everyone. In how many cases I am getting the 1? See, actually, here x equals to 1, minus 1, 3, minus 3, 5, minus 5, and 7, minus 7. In all these places, I am getting 1. So, what is my solution? Please reply, everyone. Write down in the chat window. What is the solution? 1, 3, 5, 7. Yes, is there any doubt? Hello, yes, can you unmute yourself?
Hello.
हाँ बोलो.
Ma'am, due to net issue, I want to know that in first example, why didn't you consider 6 and minus 6?
I have not written that. See, when you perform the 6 square mode at, what you get the answer? Yes, 6 square mode 8. What you get
Thir-
answer?
36 mode 8, you mean?
So what you get the answer?
Uh, 4.
So see, actually, what is the definition here? So here I have written x square congruent 1. See, I am assuming that what is my question? I want to find the square root of 1 mod n. So I am assuming it is congruent to x because I am putting the different value of x. And see, when I can say x square congruent 1 mod 8, if I am performing x square mod 8, and if I am getting 1, then I can say that x square congruent 1 mod 8. Yes, is it clear?
Yes,
So
yes, ma'am. I know.
yes,
Actually, I
so
was.
yes, that's why I'm telling you in 6 and minus 6, if I am performing the square, I am with means you get 1 or not. You are not getting 1. So that's why I'm not considering it.
No, ma'am. I am asking out first example. 7. In last example, 6 were 36 mode 7. You will get answer 1 in last example.
Okay, just wait. So you are talking about this one. Why we are not considering? See, we are not considering it, yes, because see, in one and minus one, both the case I am getting one. Similarly, in 6 and minus 6, also I am getting one. Right, in this case, in this particular case. But see, you know that minus one is congruent to 6 more 7. What is the meaning of it? If I am performing minus 1 mode 7 or I am performing 6 mode 7, I am getting the same answer. Yes or no?
Yes, ma'am.
So that's why either you write minus 1 or you write 6.
Okay, ma'am. Got it.
Clear? Similarly, either you write 1 or you write minus 6. Clear? Yes, what I'm trying to say. That's
Yes,
why
ma'am.
here, that's why here my answer is 1 plus 1 and minus 1. And what the square root test says, if the number is prime, then finally what you get the answer plus 1 and minus 1. And we are getting the same answer here. Now clear? Here my number is what? Prime. And here I am getting the same answer plus or minus 1. Is it clear what
Okay.
I'm trying to
Yes.
say?
Yes,
Right.
ma'am.
So see, similarly here, what I am trying to explain here, what I have done, if I am putting x equals to 1 and minus 1, in both the case I am getting 1, right? In 2, I am not getting 1, so I am not considering it. 3, I am getting 1, minus 3, I am getting 1. In 4 and minus 4, I am not getting the 1 value, so I am not considering it. In 5 and minus 5, I am getting 1 value. And 6 and minus 6, I am not getting 1. And in this case, but see here, what's the answer? See, one of the student have written, I think in chat window, 1357. Generally, you are correct. And on your 8 cases in total. See, yes, 8 cases, but there are not 8 cases. Why? Now, can you explain me? Because see, here you can say that. See, I'm writing here. See, can I write in this way? Yes, right now you see it's 7 is congruent to minus 1 mod 8. Yes or no? 7 is congruent to minus 1 mod 8. So either you write minus 1 or you write 7. Yes or no, everyone? Clear what I'm trying to say? Is it clear, everyone? So that means the answer is plus 1, minus 1, plus 3, minus 3. Yes, Bhumit, you are correct. So that means, see, here I am considering what? Plus 1, minus 1, because see, see, 7 and minus 7 I am not taking because 7 is congruent to minus 1 mod 8 and minus 7 is congruent to 1 mod 8. So either you take 1 minus 1 or you take 7 minus 7. Similarly, here I can say that the 3 is congruent to what? Minus 5 mod 8 and minus 3 is congruent to 5 mod 8. Yes or no, everyone? Is it clear, everyone? Right, and that's why the square roots are what? Here I can write plus or minus 1 and plus or minus 3. Clear? So now see here that thing that I have written here. So here in this case, here the answer is plus or minus 1 and plus or minus 3. So now see the definition. If the n is composite, then you are getting plus or minus 1 and possibly other values. So is it clear? Now, see the next scenario, that is here, what are the square roots of 1 mod n if n is 22? So now see, if n is 22, so now see if x is, just I am telling you, x is 1 and minus 1, then I am getting the correct answer 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So up to 20, see, I am not getting the answer. But see, when the x is 21, so at that time what I am getting? At that time I am getting one value, right? So in 1 and minus 1, and another case is what? 21, that I am getting the one value. But all of you know that the 21 is congruent to minus 1 more 22. So that's why here I am getting only two value, plus 1 and minus 1. But see, the 22 is a what? Composite number. So, but see, here I am getting plus 1 and minus 1. So that means I can say that my square root is test is fail in this case. Is it clear to you all what I'm trying to say? Hello? Okay, so I think all are clear, right? So this is all about a square root test, everyone. So now next is the Miller-Rabin test. So all of you first write down this. I will give you a time. Quickly write down this algorithm. Okay, and based on that, I will explain you example. And regarding that proof is that, but that I will explain in next class. This Miller-Rabin proof that I will explain in next class. So quickly write down this algorithm. Once it is done, please reply everyone. There is a Miller-Rabin test to, if the question is given to you, check whether the particular number that passes the Miller-Rabin test or not. So basically we are using it to check whether the number is a prime or composite. For that we are using this Miller-Rabin. And for regarding this algorithm, there is one proof. Done everyone? Is it done? Okay. Now let's start with the example. Okay, now listen. The question is, does the does the number 27 pass pass the Miller-Rabin test? Right. Now see the one by one. We'll see each and every step. First of all, in Miller-Rabin algorithm, see the this value that you have to pass as a argument to the function. So what is the n value? N, that is 27. Now n minus 1, that is equals to 2 raised to k into m. So now see here, this is the equation. N minus 1, that is equals to 2 raised to k into m. Now what is the n value? N is 27 minus 1, that is 26. Now you can write in this form 2 raised to k into m. In this form you can write. So that is what? 2 raised to 1 into 13. Right? I can write in this way. So now see the algorithm. So now n minus 1, that is 2 raised to k into m, where m is odd. Right? So first you understand the example. So then proof is easy for you. So now n minus 1, that is equals to 2 raised to k into m. So 27 minus 1, I'm getting 26. So 2 raised to 1 into 13, where the condition is the m is odd. So now here in our case, the 13 is an odd number. Right, up to this it is done. So now here from that I can write in this way, where m, which value I'm getting? 13. Right, the k value that is I'm getting, that is 1. And what is a? The a value that is getting, that a, that is 2. Now see the algorithm, everyone. So now see here, choose a random integer from this two. So a, I am taking a, that is what? 2. So because which type of form here, a that I am taking, that is 2. Then k, that I am getting the value, see here, the k, that is 1, m, that is 13, and a that I am taking, that is 2. Okay, now then after what you have to do? So now see the algorithm, you have to apply this step, b equals to a raised to m mod n. Okay, so now I am writing here. So b equals to a means 2 value, m means what? 13, and mod n is 27. Okay, so now when I'm applying the square and multiply method, all of you know that when I'm applying square and multiply, so what I'm getting? 8192 mod 27. Right, so this value that I am getting. Now after that, see, so here what I am getting the value. So here I am getting b equals to 11. Now see here, what is the next step? So now once you calculate this b, now then after you have to check if b mod n, that is equal 1. So now here what I am getting the answer? 11. So I'm not getting 1. So that means if it is 1, then you can say that probably the number is a prime, but we are not getting this. Right, so now, so b is not congruent to 1 mod n. Right, can you write in this way? Because now, I'm not getting 1, so here I can write in this way, b is not congruent to 1 mod n. Right, so now after that what you have to check? So according to the algorithm, now this step is applied for I equals to 0 to I less than equals to k minus 1. So in our example, the value of k is 1. So 0 to 0, this loop is repeated, and at that time you have to check if the b mod n, that is equal minus 1. So we are not getting this. So at that time what happened? It is not a minus 1. So that's why this else part is executed, and what we are getting? B equals to b square mod n. So b equals to b square means, so now see here, b equals to b square mod n. Right, so now what is our b value? So the b value is what? 11 square mod n is 27. Right, so here what you are getting? Here you are getting 13 value. Right, and that's why here I can say that see, I'm performing this b square. Right, and see finally it will print the message, the n is a, because see I equals to 0 to 0, and after calculating this it will print the message n is a composite number. And see, according to our algorithm, and obviously all of you know that the 27, it's a composite number. So my algorithm says that it's a composite number. right? So again I repeat, any number is given to you. See, right now you know that this is a composite number, but by using this algorithm I want to print it. Okay, it's a composite number. So what is the first step of algorithm? What you have to do? First you have to write in this form n minus 1 equals to 2 raised to k into m. So what I have done here, so I am writing 2 raised to 1 into 13, and in this case m is the odd number, so here 13 is the odd number. So I am getting m is a 13, k equals to 1 and a equals to 2. Now after that you have to perform this step, b equals to a raised to m mod n. Now when you are calculating this, see here, when I am performing the square and multiply method, I am getting 11. So now when I am getting 11, so now here if it equal 1, then I can say that it is prime, right? So in our case it is not congruent to 1 mod n. So now this portion is calculated, I equals to 0 to 0. So at that time, see, the b mod n is not a minus 1. So that's why I can, that's why the else part is executed, and which value I am getting, b equals to 13, and finally the algorithm print the answer, the number is a composite. So is it clear to you all how my algorithm work? Is it clear to you all? Please reply. Okay. So now see, this proof that I will explain in next class. Now, okay, here the another question is there. See here quickly, everyone. Does the number 561 that pass the Miller-Rabin test? So here what I am doing here, n equals to 561. So I am writing in which form? N minus 1, that is 560, 35 into 2 raised to 4. I am writing in this form 2 raised to k into m, where m is what? M is an odd number. So now here what I am getting value, k equals to 4 and m equals to 35. Let's use a equals to 2, right? A equals to 2, so b equals to a raised to m mod n. So now 2 raised to 35 mod 561. So according to square and multiply method, what I'm getting, 263. And all of you know that according to the algorithm, you have to check whether this b mod n that is equals to 1. Here I am not getting 1. So that means the algorithm will enter into the for loop. Is it clear up to this, everyone? Right, here I am not getting the 1, so that means the algorithm get into what goes into the for loop. So now in this for loop, what you have to check? Now see, so here what is the value of k? K is 4. So from 0 to 3, the loop is repeated. So now what I'm doing here, I equals to 0. So when I equals to 0, so at that time which portion is executed? All of you know that b equals to b square mod n, because see, in our algorithm this is a step. So if you are not getting this 1, then this for loop is executed, but here b mod n is not, if minus 1, then directly it executes the else part. Okay, so similarly here in this case what happened? See the example. From 0 to 3, the loop will be repeated. B equals to b square mod n. What I'm getting, 166. Right. Again for I equals to 1. Again I am taking the value of b equals to 166. Again it is not equals to this. Right. So I'm repeating this loop. Okay. And finally at I equals to 3, I am getting 1. And if I am getting 1, then now the algorithm will come out from the for loop and will say that the n is a composite. Is it clear to you all? Hello? Any doubt, everyone, in Miller-Rabin test example? Right, so in this way, the any question can be asked in exam. Each and every step of algorithm that you have to explain, and based on that, you have to say that whether the algorithm, whether the number is a composite or prime number. Clear? Okay, thank you, everyone.